People have known about this need for a long time, and that is to go into environments that are conventional robots typically foul up their mechanisms that they're trying to move with. Their legs and their wheels typically get jammed up with dirt or contamination, or worse, if you're going down into some kind of a rocky area, they'll just get stuck. They just can't propel themselves through it. The most obvious one is like earthquake situations where you have a lot of rubble that's collapsed, buildings have collapsed, and they need some kind of autonomous system to go down in there and look for survivors. And most of the robots that go down into these rubble scenes, they generally don't function very well, and they usually only make it about 10 feet and then they stop and they never get them back out. I think almost all of them are lost when they do that. So we thought, it'd be neat to come up with something that didn't have such a structure to it, that would sort of adapt to the environment, change its shape as it went down through the various holes. And so I came up with, well, then we want something kind of amorphous that's sort of squishy, like filled with gelatin kind of example. That would certainly meet that need. But in terms of NASA's needs, we also thought it might fit well on these very dusty locations like Mars and the Moon, which have historically had great rover experience there. And the rovers, their biggest problem there has always been getting stuck in the very loose sand. Where if you had something that would sort of just inch its way along or roll its way along on the surface, you could get rid of that problem, we feel. What I didn't want to have happen is design the same old things that everybody else has already done. So we got to start with some fresh ideas. Otherwise, we're never going to stumble on the right answer. And I felt like the right answer is not out there right now. In terms of people working on it, we had about 5 summer students that helped me on it. We knew it was a tough problem. If it wasn't a tough problem, it would have already been solved. A lot of people looked at it. And we confirmed that. It is a tough problem. We tried some hands-on things and some simulations. So we sort of had to juggle, what's realizable in a lightweight system that can be deployed, that's not too expensive. So we juggled a lot of those different factors.
The first idea was to take a electromagnetically stimulated ferrofluid and inch a bladder bot across the surface. The silver part here in the picture shows the electromagnet. The bladder itself is filled with a ferrofluid, which is then stimulated and basically squished through, projected itself forward. In the second case, we looked at electromagnetic polarity reversal. So there's 4 electromagnets here. Initially, they're all opposite in polarity, and then you change the polarity of the lead ball to get it to repel from the other 3, and then you attract them one at a time to draw the bladder back together. And you can see this better from the top-down view, where we show how these magnets change polarity in real time. The third idea was to use polymers, either electrically or thermally stimulated, basically like a multi-stage airbag. And you'd collapse some of these stages basically by either cooling them off or heating them up or electrically exciting them, and then get the object to roll over in some controlled fashion. And this process would repeat and allow the bladder to move along the surface of the planet. The next idea was to use a quad valve fluid flow system. And this was pretty simple. Basically, the liquid sits in the bottom. You pump it out through to the side, and it rolls the bladder over, and then you let all the liquid sort of settle in that new compartment, and then the process repeats over and over, and it rolls itself along.